equilibrium. So last time, we started talking about if we have the known equilibrium constant and initial concentrations of a mixture, we can then solve for the equilibrium concentrations of whatever it is that we're looking at, right? So last time we can solve for equilibrium concentrations if KEQ is known. And so we always start this by setting up what's called an ice table. And if we have some reaction that's A plus B goes to C, it's an equilibrium. An ice table looks something like this. And I stands for what? Initial, right? These are initial concentrations. These are initial concentrations. C stands for the change in concentration. And then E was the topic of the chapter, the next two chapters, equilibrium. These are going to be our equilibrium concentrations. Right, so we set this up, and that allows us to get an expression for our equilibrium concentrations if KEQ is known, for example. And so in a case like this, for a arbitrary reaction like this, what would be our equilibrium constant? How would we, how would we write our equilibrium constant? What would KEQ or KC be equal to here? KEQ, put slash C, because you'll see both of them used like that. C over A and B, right? Because they all have a stoichiometric coefficient of 1, and so they don't have any exponents, and that's all equal the ratio of the products over the reactants. So in this case, if we started with 0, we'd probably have to set up a more complicated expression. We couldn't start off with 0 of C, because then, actually, yeah, we could start off with 0 of C if we did something like this. And so to get these equilibrium values, you just add up the change and the initial values, and then these get plugged into our expression for our equilibrium constant, right? And so that's pretty much all we talked about last time. You can do this in terms of concentrations, or you can do it in terms of what else, if you have gaseous reactants. Partial pressures, right? So you can also, I'll put in, or for gases, you could have something like Kp is equal to partial pressure of C over the partial pressure of A times the partial pressure of B, right? So you could do this in two different ways, and we went through an example last time. We didn't have to put it into the equilibrium constant, but we used facts about adding up pressures of ideal gases, right? So you can do this in terms of that. And then what states of matter are included in the equilibrium constant? We also talked about a little bit about heterogeneous equilibrium. Or I should say, what states of matter are not included? Huh? Solids and liquids, right? Those are not included. And we did that in lab last time to look at the solubility product for a complex ion equilibrium. Well, if we have time, we'll get to that in lecture today as well. And that's related a lot to what we're going to be doing over the next couple weeks in lab. So this part of the semester is just the really smelly part, because the qualitative analysis labs, each one takes about a week to do, and they involve a lot of testing different solutions, and a lot of the reagents and stuff are kind of smelly. So another reminder just coming up is just make sure that you have appropriate PPE on, right? So no crop tops, have your hair back and stuff, because some of the stuff we are dealing with is a little corrosive or just not fun to get on your skin, and it smells. All right, so that's what we include in our equilibrium constant. Okay, so here we have an example of hydrogen sulfide that decomposes at room temperature. It's placed in a flask at 25 degrees, and it's what is the total pressure of this, of the pressure in the flask when we allow this to happen, right? So think about the different states of matter, your expression for Kp here, and then how are you going to use that to solve for the total pressure? All right, so what? Need to set up an ice table for this necessarily, but we want to find the total pressure of the system, and what can we relate to Kp? All right, we want to set up an expression for Kp, right? We want to relate that to the total pressure somehow. So that's the first step. See if you can set up an expression for Kp. Kp is equal to, right? So we have this example here that we did in a little review slide. Set that up for this chemical reaction. So what is Kp equal to here? The products over the reactants, and specifically, when we say the products of the reactants, what are we talking about? What of the products and what of the reactants? So we can do it in terms of concentration, but here you're given Kp, right? And Kp can be expressed in terms of what? Of the reaction. The pressures, if we have gaseous reactants in the problem. Do we have gaseous reactants? Yep, just the products, right? Which means that Kp will just be equal to the partial pressure of NH3, hydrogen sulfide. And do we include the partial pressure of NH4 HS? Why not? Because it's a solid, right? We don't include solids in our expression for equilibrium constants. So this is just equal to P NH3 P H2S. And so if we're starting off with just 0 of our products in this case, so all we're doing is just allowing this solid to decompose, what can you say about this? How can you simplify this farther? I'm going to go to the next slide. But we don't have to set up an ice table, but if we did, if we just set up an ice table, we start off with some amount of NH4, S, NH3, H2, S. How much do we start off initially of each of our gases? Or we just put ammonium hydrogen sulfide in a container and let it decompose. All right, so how much do we start off initially with? Bless you. Morning, Alex. 0, right? We should start off with 0 of each of these. And we can start off with some amount of our ammonium hydrogen sulfide, but we're not given that, and that's not really relevant for the problem because that doesn't affect the position of the equilibrium at all, right? How much ammonium hydrogen sulfide is there doesn't affect the position of the equilibrium, so we don't really worry about that. And on our way to equilibrium, we have how much change in both of our gases? Right, what is the change? How do we represent that last time? It should be positive, right? Because we're starting off with 0, right? So if we start off with 0 of our products, Le Chatelier's principle, or if we look at our reaction quotient, that was the other thing we talked about last time, that tells us that the reaction is going to move towards the products, right? So we should have a positive change. And what do we use to represent that change? We can use some variable x, right? And then should it be plus x, or do we have to include any other coefficients there? No, because the stoichiometric coefficient for all of them is just 1, right? So for each of these, we just have a coefficient of 1. So we don't have to include plus 2x or anything. For every 1 molecule of ammonium hydrogen sulfide that decomposes, we create 1 molecule of ammonium gas and then 1 molecule of hydrogen sulfide. Right? And so then at equilibrium, again, we don't have to worry about our solid because it doesn't affect the position of the equilibrium. We then have that each of the concentrations, or in this case, not the concentrations, what does X represent? These represent the partial pressures. And again, the reason that we can do this is because of the ideal gas law. We can write the concentration in terms of the pressure of the gas, right? The concentration and the pressure are related to each other. Again, remember, so we have P over RT equals N over V, right? The moles over volume is just the concentration, and that's related to the partial pressure. Kp was the equilibrium constant when we're looking at pressures in terms of gaseous reactants, right? So X in this case represents the partial pressures at equilibrium. And so then where do we go from here? Where do you guys think we go from here? Yeah, we have a value, right? Where is it? Right here for Kp. And we have an expression, right? This is equal to Kp, right? And these represent the partial pressures at what? Equilibrium, right? And that's exactly what we just did with the ice table, right? These represent the partial pressures at equilibrium. I say you don't have to set up an ice table for this because you can just look at this and realize that, well, if I start off with 0, the amount of ammonia and hydrogen sulfide has to be the same for both of them. Why? Because just the stoichiometry in this case, right? If I start off with 0 of those 2 gases, then whatever I create has to be the same for both ammonia and hydrogen sulfide. And so I'm going to go to the next slide. So then we plug into expression for Kp, right? So we can plug in the X values if we want. So we get X times X because they're equal to each other. This is the same thing as saying the partial pressure of ammonia gas is equal to the partial pressure of hydrogen sulfide. This is equal to 0.108 is equal to X squared. So I solve for X by doing what? Yep, we square root both sides, which is the same thing. This is equivalent to just 0.108 to the 1/2 X squared to the 1/2. And so we get X is equal to 0.108 to the power 1/2. 0.108 square root. So we get x is equal to 0.327. And what would the units of this be? Or what would you guess? KP doesn't technically have any units, but we know the units because we know what we're solving for. What were we solving for again? Pressure. We can use atmospheres, or if you wanted pascals, you could write it like that. It would just be changed by value. Usually when we're doing problems like this, everything will be done in atmospheres, right? So we plug that into our expression for the equilibrium constant in terms of our partial pressures. And then the question asks us, what's the question actually asking us? What does the question want us to solve for? We want to find the total pressure of the flask. And how do we get the total pressure once we have X? Yeah, we add the partial pressure, right? We know these two pressures are equal to each other, so we just add them together. So we find the total pressure, which is equal to P NH3 plus P H2S. And then we know that P NH3 equals P H2S, and those equal X. So this is just 2x if we just add those two values together. So we get 0.657 atmospheres. All right, all we did is we just solved for each individual partial pressure, but because we know pressures add together to form the total pressure, then we just add those values together. Right? This wouldn't be the same necessarily for a solution, because solution we have a constant volume when we do that, right? So they don't just add together to get we wouldn't say the total concentration in solution. All right, so this one, again, we don't have to use any complicated. We don't really have to set up an ice table for this one, but it makes sense in terms of the equilibrium discussion, right? We're looking at the change to equilibrium. We know we start off with 0 because it says ammonium decomposes at room temperature. This means that our product's pressure is 0 initially. Right, but for these equilibrium problems, it's never a bad place to start just by setting up an expression for your equilibrium constant. Then if you have this expression, you kind of just stare at it for a bit. You're like, I don't really know where to go next. Think about what do these values each represent, right? Kp I'm given in the problem, right? So I know I need to relate something to Kp. Then think about these are partial pressures, and specifically they're the partial pressures of each gas at equilibrium. Any questions on that? How do you feel about that? Thumbs up, thumbs to the side, thumbs down, thumbs up, thumbs to the side. Okay, let's do another one. Does anyone still need these slides, or still looking at the notes here? No. Okay. I guess I accidentally made another page. All right. So here we have another one, except here we're given the value of Kc. It says at a relatively high temperature, the following reaction can be used to produce methyl alcohol. If the concentration of carbon monoxide at equilibrium was found to be 0.01 molar, what would be the concentration of H2? All right, so let's think about this and start by setting up an expression. For what? Yeah, we'll set up an expression for Kc. What is our expression for Kc here? What is it represented in terms of Kc? Products, and what of the products and what of the reactants?
Product is CH3OH, but that's a liquid.
Mm-hmm.
And then the reactants are both gases.
Mm-hmm. And Kc, what is Kc expressed in terms of? Is it in terms of pressures or concentrations? Concentrations, right? So whenever we see the C, that tells us the concentrations, right? So it's concentrations of products over reactants, whatever their stoichiometry is. In this case, we don't include methanol because the methanol is liquid, right? So we don't include that in our expression for our equilibrium constant. So what is our equilibrium constant then? We have the concentration of carbon monoxide, the concentration of H2 to the power of 2, and this is all over 1, right? Because we have products over reactants, we don't have anything on our product side because it's in a different state of matter, right? So this is not liquid, is not included. All right, so this is our starting point then for this problem. And what else does the problem give us? Yep, it gives us the concentration, right? This tells us the concentration of CO at equilibrium is 0.010 molar, right? And what else are we given? For the reaction, what else are we given?
KC.
We're given the value of Kc, right? So we're also given Kc, right? And we know our expression for Kc is equal to 1 over CO H2 squared. And we want to solve for what? Think of H2, and what do we want to solve for H2? Yep, we want to solve for the equilibrium concentration. So if we're given these two values, we came up with an expression that relates all three of the things that we're looking at here. What do we have to do? Yep, we just have to solve for H2 in this case, right? So this one, nothing tricky. Go to the next page. We just need to solve for the concentration of H2 at equilibrium. All right, so if we have Kc equals 1 over CO H2 squared, we can do this algebraically and then plug in all our values at the end, or you can plug in values from the beginning. So how do we get H2 isolated here? What's the first thing we should do? We can do that. We can move the concentration of CO to the other side. What happens to the concentration of carbon monoxide on the right-hand side? They cancel out. So we get CO Kc is equal to 1 over H2. What do we do next? H2 squared. we can just invert this. Alright, we could have started by multiplying h2 squared to both sides in step 1 if we wanted to, but we can do that here. We can divide both sides by CO, KC, CO, KC, right? And then simultaneously, we can multiply by h2 squared, right? On the left-hand side, these cancel out, and on the right-hand side, the h2 squared cancels out, right? So we don't have to start with doing this step, but if we did, that's fine. We can still isolate h2 the same way here. So we get h2 squared is equal to 1 over CO KC. And then what do we have to do?
Plug in the numbers. Plug in the numbers.
We can plug in the numbers if we want. We can do h2 squared is equal to 1 over 0.0100 molar times 13.5. Right, if we do that, then we get some value in the denominator, 1 divided by 0, 1 divided by 13.5. This will give us something like 7.41. And are we done there? No, why?
Squared.
We still have, this is solving for the concentration squared. So now how do we isolate that?
Square root.
Yep, square root both sides or raise both sides to the 1/2. So if we square root this, that gives us, go to the next page, we get h2 is equal to about 2.72. And this is a concentration, so we know it's going to be in units of molarity. All right, so we don't have to do an exact way to isolate H2 in this algebraic equation. All we have to do is we just have to keep track that whatever steps we're taking, they make logical sense, and then we end up with the right value at the end, right? We know we're solving for H2, not H2 squared, so we have to make sure that we square root it at some point, and we can isolate it a couple different ways, right? In a number of different steps. Nice thing about multiplication and division, it doesn't really matter what order you do things in. All right, so this one, again, we're given, well, this one is slightly different than the one before because we're not given an initial concentration. We're given an equilibrium concentration. We're given an equilibrium constant. And we know that since there's no liquid included in our equilibrium concentration or equilibrium expression, we can then solve for the other equilibrium concentration here, right? If we had another product that happened to be gaseous, then we wouldn't be able to do this. We wouldn't have enough information to then solve the problem, right? But because the nature of the physical states of each of the reactants and products in our chemical equation, our mixture of liquids and gases, that allows us to then simplify the problem and then solve for it, right? So here, the tricky part is really just identifying what's given to you, and given what you know, can you set an expression to relate all of those things together? All right, any questions on that one? All right, so again, these are kind of the more easy equilibrium problems, right? So if there's any questions, I want to make sure we address those. And it can be related to some of the examples we did last time too, with the partial pressures, or with just solving for equilibrium concentrations given Kc. Right, Kc represented what? Now I'm just reviewing. I'm just asking you. Like if it was an exam, what is Kc? What is an equilibrium constant? What is equilibrium? Yeah, when the forward and reverse rates are equal to each other, right? So reactions are still happening because we call it a dynamic equilibrium, but what's staying the same? The concentrations are staying the same in this case, right? So the concentrations are staying the same, but the reaction is still happening. And Kc represents the ratio of those concentrations. Do the concentrations at equilibrium have to be the same for every initial concentration? No, right? So the equilibrium concentrations don't have to be the same. You can have different mixtures, but the ratio that they reach, once they reach equilibrium, the ratio of them is what stays the same, right? So the equilibrium stays the same no matter what the initial concentrations are, but the equilibrium concentrations themselves can be different from each other. And so when we talked about QC last time, I guess that was in part 2. We finished up part 2 last time. Right, so when we equilibrium part 3, equilibrium part 2, right, when we talked about QC, right, we can have different initial ratios of products and reactants, but once they reach equilibrium, those are always going to reach the same ratio. And what that means is that the concentrations can be different at equilibrium, but the ratio of them raised to their stoichiometric coefficient has to be the same. Right, and when we looked at the plots of how concentration changes with respect to time, let's see if we have any in this one. It must have been an equilibrium. Part 1. Right, this was the equilibrium condition here. So when the rates are equal to each other, and then we also can look at how the concentrations vary with time. Let's see if I can find right here, right, we reach this equilibrium state. The actual values of where this equilibrium are at can be different, but when you take the ratio, then they have to be the same. Right, so when we're looking at these problems, it's important to keep in mind here that you're given an equilibrium concentration, because that tells you can directly relate it to the equilibrium constant. Whereas in the previous problems, for example, here you're giving some initial concentration, right, because it's implied that these are at 0, and then you have to relate those to the equilibrium concentrations, or in this case, the pressures. Right, so a lot of this is just kind of decoding what the question is asking for based off of what you're given, right? And the reason I'm just emphasizing this so much is because the math for these ones are simpler, and then once we get into being given initial values for all of the reactants and products, the math becomes a little more complicated, but the idea is exactly the same, right? The idea is exactly the same. We're just looking for something to plug into the equilibrium constant. And that's what the ICE table helps us do, right? So the ICE table here tells us, okay, well, we just plug in these values for X into the equilibrium constant, right? And then we can solve for X, and that allows us to solve for what the equilibrium pressures were, which then allows us to get the total pressure in this case. When we have more complicated examples, then you're gonna have initial values. X will change all the products and the reactants, and then you relate that to the equilibrium constant. So it's the same idea, right? And so to do those types of problems, you're gonna have to use quadratic equations. Right, are there any questions on what I just said? I know I said a lot of words in a row. But... All right, so for these more complicated problems, we're gonna be using the quadratic equation. I think that's a T. Equation, does anyone remember what the quadratic equation was? I know you guys have probably seen this a million times since maybe early high school, but it's minus b plus minus the square root of b squared minus 4ac divided by 2a. All right, so this is what we call the quadratic equation. This really isn't a quadratic equation. This is the solutions, the general form of a solution to a quadratic equation. Right, so what is a quadratic equation? How do you know if you have a quadratic equation?
Like x squared.
Yeah, if you have the highest power in your equation is going to be x squared, right? So a quadratic equation is the highest power of the variable is 2, right? So x squared, for example. Right, so even that partial pressure problem was technically a quadratic equation, right? Because we had x squared was equal to kp for those pressures. That's technically a quadratic equation. It's just all the other coefficients besides a in this case would be equal to 1. Right, so it was kp was equal to x squared. That's technically a quadratic equation where b and c are equal to 0 in this case. And all we have is a. And so the general form for a quadratic equation is going to be a x squared plus b x plus c is equal to 0. Right, so you use the quadratic formula, which gives us the solutions to the quadratic equation. You have to get the equation into a form like this, right, where we try and find a coefficient for the first power of x, coefficient for the second power of x, and a coefficient for x to the power of 0, right? This is the same thing as writing x to the 0 right there, right? X to the 0 is just equal to 1. And so once you have that, you get two solutions. And again, we talked about this briefly last time because when you plot something that looks like a quadratic equation, usually it's a parabola, and these solutions are just where this parabola intersects the x-axis, right? So this is the x-axis, and that's our y-axis. That's how we interpret the results of the quadratic equation. And you just plug them into minus b plus minus, right? So that's where we get the two solutions from. You have one solution that's plus the next term, and then one solution that's minus the next term. So that's b squared minus 4ac, all of that divided by 2a. Right, so x1 could be related to the plus the square root term. x2 would be minus the square root term. So in general, we want to move things or write things in this form. If it's factorable to, you can also say that each root is equal to what the factor is, right? So you can factor quadratic equations. So I'll put it over here. If you can get it to x minus x1 times x minus x2 equals 0. Right, if you can factor the equation, then that gives you that x1 is one solution and x2 is also a solution. So there'll be cases where it's easier to analyze the answer in terms of that, and sometimes you're going to have to actually use the quadratic formula to solve for that. The simplest one is where you don't have any, b is equal to 0 and c is equal to 0, so then you just square root both sides. That's the easiest way. But even when you square root both sides, that's technically still two solutions. It's just one's going to give you a negative value and one will be a positive value is what that looks like. And so that's why we don't ever write plus minus in our answers there, because if we're looking at concentrations and pressures, what can we say about the negative value? This corresponds to a parabola that looks like this potentially, right? And let's say this is the partial pressure. What can you say about this value? Right, this is 0, 0. it's negative, right? And negative pressures don't make sense, don't make physical sense, right? So this is negative value, so it doesn't make sense or physical sense. And so with the quadratic equation, you have to look and see which one of my solutions makes physical sense and which one doesn't. All right, so this is just a brief review of how to use the quadratic formula, which is this right here, to solve a quadratic equation. All right, so here's an example, right? So now we're going to apply this to equilibrium. So we have this reaction. Initially, a mixture contains 0.2 molar N2 and 0.02 molar of O2. All right, so we're given that it only has our two reactants initially, and they're at a certain concentration value. And we're given the equilibrium constant at whatever temperature this reaction is happening at. And then we want to find the equilibrium concentration of the products and the reactants here. All right, so we can always start with just writing our equilibrium. Not equilibrium concentration, our equilibrium, writing an expression for our equilibrium constant. For Kc in this case. And what is Kc related to for this problem? Or what is Kc related to in general? If we see subscript C, that tells us we should be looking at the concentrations of the different reactants and products here, right? So this is going to be related or proportional to the equilibrium concentrations of products / reactants. And so what is Kc equal to here? Yep, concentration of NO to the power of 2 divided by concentration of N2 and O2, right? Everything's in the gas phase, so this is homogeneous equilibrium. Every term is included in our equilibrium constant, right? And we know that this value is given to us, Kc, and we know that each of these concentrations represent the equilibrium concentrations here. Right? So the next thing we need to do is find an expression for the equilibrium concentrations, right? Because what are we given? Mm-hmm. Mm-hmm. And what kind of concentrations are those? So these are the initial concentrations that we're given, right? Because here it says initially the mixture contains these two, right? So this tells us that these are our initial concentrations and not equilibrium, right? So that means that we can't just plug in these concentrations into our equilibrium constant, right? Because these are the concentrations before the reaction has reached equilibrium. And so how are we going to solve for the equilibrium concentrations? Yeah, that's exactly what we're going to do. We're going to use an ICE table, right? So to do this, we use an ICE table. All right, so I'm going to write this reaction on the next page. We have N2 gas plus O2 gas is in equilibrium with 2 NO2 gas. And we set up an initial change in equilibrium. And so we'll see when we set up the ICE table why we don't just plug in these values, and just because we start off with no NO here, why that doesn't necessarily simplify the problem the way it did in the past, right? Because we have two reactants here that each start with a different value, right? When we're looking at the pressures and stuff before of a decomposition of one reactant into a product, we knew, okay, we started off with 0, so that means that whatever I make of one is whatever I lose of the other. Here we don't know what this concentration is going to be at equilibrium. Okay, so what is our initial value for each of these reactants?
For both
Mm-hmm.
N2 was 0.200.
0.00 molar, 0.200 molar, and then our initial for nitrogen dioxide was 0, right? Because we started off with none of this. And now we need to find what are these values going to be at equilibrium. And so how much do we lose of each of our reactants? Yep, we lose minus X, right? That's our change. And what about for O2? It should be minus X as well. And how can we know it's not minus 2X or minus 3X? Yep, the coefficients are both 1, which means that for every reaction, or every mole of reaction that happens, for every one N2 molecule I use 1 oxygen molecule, right? And what about for our product here, nitrogen dioxide? It should be plus 2X, right? Because we're increasing the concentration of nitrogen dioxide. And for every reaction that happens, or every mole of reaction that happens, we create 2 moles of our products. And so then we get the equilibrium values just by adding up whatever's in our initial and our change, right? So we get 0.200, 0 minus X, 0.200 minus X, and then plus 2X. All right, so these are our equilibrium concentrations now. And this is what we wanted to solve. And so why did we want to solve for this? Why did we need these values here, or these expressions? Yep, for our expression for Kc, right? So all of this goes into our expression for Kc, which was NO2 squared N2 and O2, right? These are the specific values or expressions that need to now go in here because these all represent the equilibrium concentrations. So we get 2x squared over 0.2 minus x times 0.2 minus x. And this just simplifies to 2x squared over 0.2 minus x squared. Right, these are the same thing, so I just combined them into one. Right, so now we have our expression in terms of our equilibrium concentrations. The only thing is we don't know what x is yet, so we have to solve for that to then be able to solve for the equilibrium concentrations, right? Because each of these equilibrium concentrations isn't exactly equal to x, they're related to some expression with x in it, right? We know that whatever the change is on the way to equilibrium, we're just going to subtract that from our initial values, and then whatever the change is for our product here is just 2 times whatever that change is. Diego?
So is that when we use the equation for that?
Yeah, so that's when you're going to use the quadratic formula, except we have to rearrange this now, right? Because it doesn't look like, right, it doesn't look like anything like this, right? We can't really figure out what A, B, and C are. So we have to rearrange this first, and once we rearrange that, then we can use the quadratic formula. All right, so who has an idea what's the first thing that we're going to have to do here?
Square root of both sides.
We could square root both sides, yeah, that'll make it a lot easier. So if we square root both sides, the only thing you're assuming there is that x won't equal 0.2, right, so it doesn't blow up. So if we do that, then we're not gonna have to use the quadratic formula, but we can square root both sides, right? If we square root both sides, that'll give us the square root. And the reason that you can do this is because kc 2x squared 0.2 minus x squared is equal to 2x over 0.2 minus x squared, like that. So you square root both sides. 1/2, 1/2, that gets rid of the square on the left-hand side, or on the right-hand side, sorry, times 0.2 minus x. And so if you do this, then how would you isolate x here? Where would we go from here?
Would it be multiplying both sides?
Yep, we'd multiply both sides by what?
0.2.
0.2 minus x, right? So we multiply that to both sides, cancels out on the right-hand side of this equation, so we get 0.2 minus x times kc to the 1/2 equals 2x, right? So now we've gotten rid of x out of the denominator here, but we still have x on both sides of this equation. So what do we do now? We can divide by 2. So if we divide by 2 to both sides, cancels out on the right-hand side of this equation. So we get 1/2, or I'll just combine everything, kc over 2, 0.2 minus x, kc to the 1/2 is equal to x. And what do we have to do here? Yep, we need to distribute, right? The only way we can collect like terms of x on one side is if we distribute everything. So we're gonna multiply this in to the parentheses. That gives us 0.2 kc to the 1/2 over 2 minus kc to the 1/2 over 2 x equals x. And now we need to collect x on both sides of the equation. Right, so how do we do that? I don't have an idea. Right, so when we collect powers of x, that just means that we need to collect anything that has x next to it on one side of the equation. So we can add plus kc to the 1/2 over 2 x to both sides. We do that because we know it cancels out on the left-hand side. So that gives us 0.2 k to the 1/2 over 2 is equal to kc to the 1/2 over 2 x plus x. Right, so this isn't necessarily the same way that I would do this, just because this is a little bit more algebra. And you could plug in values at this point too and simplify things if you want. And so then what do we do here? Go to the next page. what would be the next step here, right? So now we have powers of x on the right-hand side of this equation. How can we use this to solve for x? If we're thinking about factoring, what might we be able to do here? Alright, so here, we factored this into the equation, right? And that's put one of those next to each of these expressions here, right? So what would the reverse look like if we were doing this on this side of the equation? What can we factor out? We can factor out x, right? So we can factor out x, and we'll have kc over 2 plus 1 in parentheses times x, right? So all we're doing is we're just doing the reverse of the step we did earlier. So we have 0.2 kc to the 1/2 over 2 is equal to, then I'll just write all the steps, kc 1/2 over 2x plus x. We can factor x out. So we get 0.2 kc to the 1/2 over 2 equals kc to the 1/2 over 2 plus 1 times x. And then what would you do from here?
Divide parentheses.
Yep, we can divide by this big expression to both sides. 2 plus 1, it cancels out on the right hand side of this equation, and all we're left with is kc, or x, is equal to 0.2 kc to the 1/2 over 2 times kc to the 1/2 over 2 plus 1. Right? And now we see that all of these values we've written x in terms of what kc is supposed to be equal to. And we see that that's going to give us a positive value. Implicitly, when we took the square root of both sides, we're saying that we get a positive and a negative solution here. And so we could just plug all of this into our calculator. I'm just going to simplify this a little bit more. 0.2 kc to the 1/2. I'm just going to factor in that 2, kc to the 1/2 plus 2. And so if I plug this in, I get 0.2, what was it, 13.5 or 0.1 times 0.1 square root divided by 0.1 square root plus 2. And I get that this is equal to 0.027. And what are the units of x here? Or what should they be? What do you guys think? All right, if we go all the way back to, all right, what does x represent here? Yeah, it's a change in concentration, right? And if we're adding it to another concentration value, then x should also be in units of concentration here. Right, so this is going to be 0.027 molarity. And this is related to the change of all of our initial reactants and our products. Right, so this, now we've solved for x. Right, so this was the long, lengthy process, right? So that's why I said this is the kind of fundamental understanding of what's going on in the problem. Setting up this expression for Kc is 80% of the way there. Everything else at this point was just doing a bunch of algebra to isolate it, right? So I know it's easy to kind of get lost in all of the steps that we do here, but the important part is really just setting this up, right? And that's why I was like, well, the math just gets harder, but it's the same idea as what we're doing before. And so now that we have x, what's the last step that we have to do? what number is the next one? 2. Yeah, we use x to solve for the equilibrium concentrations, right? Use x to solve for equilibrium concentrations, right? So the equilibrium concentration of, what was it? N2 equals the equilibrium concentration of O2, right? If we look, we see those have the same equilibrium concentration, the same relation to x, equals 0.20 molar minus 0.027 molar. 0.2 minus 0.027 equals 0.173 molar. Right, so that's how we get then solve for our equilibrium concentration of nitrogen and oxygen. And then the concentration of N2O2 was just equal to, or sorry, not N2O2. And O is just equal to 2 times x, which is 2 times 0.027 molar. That gives us, I did that wrong here, 0.027 times 2, 0.054 molarity. And now we can look at our results and see if they make physical sense, right? Our change in concentration was 0.027 molar, which is good, right? If we got something that was larger than our initial concentrations, we'd be in trouble because we'd end up with a negative equilibrium concentration. And then this value, we don't have any physical interpretation of it just yet, except if we look at our equilibrium constant. Our equilibrium constant was 0.1, right? And what does that tell us about products and reactants? Yeah, it's gonna say the reactants are favored at equilibrium, right? Because it's a value smaller than 1, right? So this is smaller than 1. I'm not gonna put much smaller. So reactants should be favored at equilibrium, right? And if we look at our values, we see, okay, well, this value is about, a little bit less than 10 times the value of our products, right? So we can say, okay, well, this makes sense based off of our values, right? If we have something that, this was 10 times larger than this, then it would say, okay, there's something wrong here with our equilibrium constant and what it says about our concentrations, our relative concentrations of the products and reactants at equilibrium. Right, so that's just kind of a way that we can double check. We don't have negative concentrations, so that's good. And our equilibrium constant is consistent with our answers. Right, so there's a lot of steps that are involved. But again, this is the main understanding of the problem. This is the same for all the problems that we did before. The only thing that's different here is now the expressions at equilibrium are a little bit more complicated. All right, any questions on that? Aurelia?
For solving for x, could we have done something easier, like algebraically?
You could, let's see, if you did something easier algebraically, if you didn't want to leave it in terms of the variables, let's see here, once you had this expression, if you had multiplied that to the other side, and then you had left, so if you didn't divide by 2 to the both sides, then you wouldn't have this fractional expression that kind of maybe makes things look a little bit more complicated. You would have started off with just this, right? If you had just multiplied, didn't divide by two from one x when you factored in this step, you would have, instead of having a two right here, you would have had a two right here and no two on the other side. So this would have just been 0.2 kc to the 1/2 and then times kc to the 1/2 plus two, right? So that extra step you didn't have to do there. You could have just left it, left the two in front of that x, because you know the idea here is you have to collect like terms or like powers of x. So you're gonna have to collect these two and factor anyway. You're gonna have to collect this and that at some point. So you could have just factored this in instead of kc over 2. You could have also put this in the quadratic formula and you would have gotten one negative answer and one positive answer. If you had, but that probably would have been even a little bit more algebra. On the next problem, we'll probably go through an example of using that. But if you brought this over to the other side and then you factored out, you know, this part of the expression, you would have got something like, so I'm just gonna put a little star. It would have been 0.2 squared minus 0.4x plus x squared, right? And this here, right, that looks like a coefficient A of 1, coefficient B of 0.4, and a coefficient of C of whatever this is squared, right? And but then you still would have had to collect like terms of 2x squared and then factor in kc into each of those as well, right? So that might have been even a little bit more algebra in this case. But there's multiple ways that you can solve these. You don't have to go through the same approach for the algebra for each of these problems. So if one way resonates with you more, stick to that. Yep, and then also like, for example, when I was grading your guys' exams, if you're showing at least reasoning or logic and how you got to your answer, you know, I try and give as much credit as I can there, right? Yeah, any other questions? All right, so let's take like a 15-minute break because I know that was a long bit of talking there. We'll come back if you guys want, or if you're bored during break, you can start thinking about this problem. And then we'll start talking about Le Chatelier's principle and just the different conditions, and hopefully finish that up before lab today. What's up?
Can we go back to the previous slide?
This one?
Yes.
Selling them.
What did you get on? 24. Yeah. So for you, if you just one problem, that would give you the credit you need, right? So I said I'll round up whatever fractional it is, right? So you get a maximum of 1 point, and if you had 1 out of 3 questions correct, then that would be 0.3, and I'll just round it up to 25. Yeah, it's not based on completing the whole thing.
I know,
It's,
but
you know,
when I
each
saw the
question
lab,
will be worth like 30% or 33 point whatever percent of your total points. So if you get, you know, for you it would be 0.3 points, but I would round any decimal up is what I would do for that.
Oh, okay, yeah, cause I saw the lab and I was like, oh.
He was saying a bunch of stuff that I wasn't understanding. I was like,
Okay.
and then yeah, we'll take
On Monday already. You know, it's okay though. I think for sure this time will be especially that my family's leaving
Oh, yeah.
and I'm having myself
Yeah.
at house. I'm gonna be all by myself, so if we lock it.
Because not worried in there. I'm very invested in it.
And then when I got out, I was like, and then I can't take pictures anymore.
All right. Why don't you guys see if you can figure out how to at least set up an expression for the equilibrium constant for this problem right here. So we'll probably start stop at just setting up the equilibrium expression, because after that it's just a lot of algebra. I want you guys to take the next 5 to 10 minutes, see if you can set that up, given the information in this problem. So I'll walk around a little bit, help you get started if you haven't been able to get started on your own. Expression for this is Kc is x squared over 1 minus x. 1.0 minus x, right? And so you rearrange this into the form of a quadratic equation. And so I'm gonna do this all in one step since a lot of you guys have already worked through the algebra, and it looks like almost all of you are on the right track. So we have Kc minus Kc, x is equal to x squared. We bring everything over to one side and we get x squared plus Kcx minus Kc is equal to 0, right? And this is the form of our quadratic equation. We use our quadratic formula, then solve for the roots of this equation, right? The solutions are the roots of that equation. So you plug that in and you'll get some values. One of them won't make sense because it'll be a negative value for the change. And then the other one will make sense because it's a positive value. And the reason it won't make sense if it's a negative value, it means that if you look at your initial concentration, right, of PCl5, if you have 1 minus x and x is negative, that means that you're gonna end up with more reactants than what you started off with, which doesn't make any sense because this is decomposing, right? It should be decomposing into the products. You can't end up with more reactants than what you started because you don't have any products when you start an initial mixture, right? So this will give, if x is less than 0, then PCl5 equilibrium is greater than 1. And that doesn't make sense because it's decomposing. All right, so we'll finish up doing this problem. We'll probably start on Thursday, just finishing up and going through the algebra for this, but I just wanted you guys to get to this spot right here. All right, so the rest of the lecture, we're gonna be just finishing up looking at Le Chatelier's principle, see if we have enough time. Let me see how many slides there are. This is a good amount to go through, but we'll see how, because it's mostly just a lot of definitions and kind of stuff that we've talked about up until this point. All right, so Le Chatelier principle says the effect of changes on the reaction can be predicted using Le Chatelier's principle, so it's a French guy, and it states that if a stress is applied to a system in an equilibrium, it will respond in a way such that to relieve the stress and restore a new equilibrium under the new set of conditions, right? And so the main point here is, for example, one of the ways you can stress the system is by changing the concentration, right? So you say you have an equilibrium established between reactants and products, and you add more reactants to the system. Well, the system is just going to respond in a way to restore that equilibrium concentration ratio, right? Which just gives us the same equilibrium constant, right? So that stays the same no matter what the initial conditions are. And so we can stress the system in a number of ways. We'll talk about the different ways that we can stress the system. Give you guys a second to finish writing that. And once we stress the system, it's just going to respond in a way to make itself happy again, right? So like most things in nature, you disturb it, it's going to eventually relax to a state where, you know, things are not changing anymore. And so what are the different ways that we can stress the system? Well, one would be the one I just said, which is what? Adding reaction or changing the concentration of something, right? So we can change concentrations. If we think about gases, does anyone have any other idea how we might be able to stress the system or affect the equilibrium? What do we deal with when we're dealing with gases? Change in temperature will be one. I'll put that as 3, right? Change in temperature. And yeah, so for the gases, it would be change in pressure. So this would be for gases. And a change in temperature, that's gonna end up depending on the energetics of the reaction. Is it exo or endothermic in these cases? And so for the first thing, if we change the concentrations, right, we can be adding or removing products, or reactants, right? So one way we can change concentrations by adding something. We can also, if we had a special type of filter, be able to filter only a certain reactant or product in this scenario. So for example, if we were to increase A, for example, to restore the ratio, right, of products over reactants, the reaction would then shift to the right to then keep that equilibrium ratio the same. If we were to decrease B, right, so we were able to take B out of the reaction somehow, then the reaction would shift to the left to then restore that ratio, right? If we're lowering the number of reactants, we want that same equilibrium ratio, which means that we need to make more reactants to then keep that ratio, right? So Le Chatelier's principle is more of an intuitive approach to the problem. As we add something, the reaction is going to move in the opposite direction of whatever it is we're adding. Or if we reduce something, the reaction is going to move in the direction of that reduction of concentration. And this works on both the product or the reactant side. So we could do the same thing for D or C in this case as well. And so if we're adding a reaction, the reaction is always adding a reagent. It's always going to shift in the direction that tends to lower the concentration of the reacting species, right? So if we're adding a reactant, then the equilibrium is going to shift in the direction that's lowering that, right? You think like, okay, if I add too much of something to get that to not affect the system as much, I'm going to move the reaction in the other direction. And so when the concentration of the reactant is increased, the equilibrium shifts forward, right? So if we're looking at K, which is now our perturbed equilibrium system, right? We've stressed the system a little bit. Now we've added more reactant to the system. So how should Q compare to K? Right, if Q, right, if we think about our reaction quotient, it's products. So let's say we have A plus B goes to C. Our reaction quotient is equal to concentration of C, A, and B. All right, that's our reaction quotient. If we add a bunch of A to the reaction, that's initially at equilibrium, how is this value going to compare to our equilibrium constant? It should be smaller, right? Because if we're adding a bunch of A, we're dividing it by a larger number, which means that this whole thing should be smaller than what it is at equilibrium, right? And that's what we're comparing, the equilibrium constant to our reaction quotient. So that should be less than. When the concentration of a product is increased, the reaction shifts in the reverse direction, right? Because if we increase C, right, we increase the amount of C we have in our reaction, what happens to this ratio? Does it get bigger or smaller? If C goes up, it gets bigger, right? Because we have a bigger number in the numerator. And comparing that to equilibrium, right, if C goes up, that means that this should be larger than our equilibrium constant. Right, so Le Chatelier's principle makes sense in terms of our reaction quotient. How far are we from our equilibrium concentrations? And what about if we're removing something, right? If we think about our arbitrary reaction again, we get Kc is equal to C, A, and B. And so equilibrium is always going to shift in the direction that tends to increase the concentration of the removed reactant species, right? So you think if we have a drain under one of the reactants, right, the concentration or the reaction is going to shift to then fill up that drain, if we think about it like a sink or something like that. So if we look at, sorry, this should be QC, not KC. If we look at our reaction quotient, and let's say we're looking at our reactants, if we decrease A, what's happening to this ratio? Is it increasing or decreasing? Right, if we decrease A, right? This number is getting smaller, we're dividing by a smaller number, which means this whole thing is getting larger, right? So that means that our reaction quotient should be larger than K, or because we're dividing it by a smaller number. And that means that it's gonna move in the direction of the reactants. Right, because we need to create more reactants to make it reach that equilibrium ratio, which is what K is. If we decrease C then in our numerator, this number gets smaller, what happens to the ratio? Yep, the ratio then also gets smaller because we have a smaller number in the numerator, right? So if we had 2 over 1 originally, it goes to 1 over 1, 2 is larger than 1, right? So then QC is going to be less than the equilibrium. We're going to shift towards making those products. All right, so we can rationalize it in terms of, we think about like a sink analogy, you put a hole under one of the products or reactants, the reaction should flow in the direction that fills up the drain or the sink. And then we can also think about it in terms of our reaction quotient, right? Mathematically, if we increase or decrease one of these terms in this ratio, how does that compare to what the equilibrium should be, right? And so we're thinking here we have a system that's already at equilibrium, and we're trying to mess with that system, right? So that's why we know how it's compared to the equilibrium ratio. Okay, any questions on that? All right, so here we have an example, but we'll go through something like this first, right? So we have our reactants in our products here, and we'll see if we can predict the direction of the shift, right? So if we have an increase in concentration of Cl2, right, which direction is the reaction going to shift? All right, so everyone can point that way or that way, left or right. It should shift to the products, right? Because as we're adding more of this, right, to keep the ratio the same, we need to move the reaction in this direction to then keep that ratio the same, right? So that should be a shift to the right. What about if we're decreasing the concentration of chlorine? Left or right? Right, that should shift to the left, because if we're draining Cl2 here, the reaction is going to flow in that direction to then fill up that drain, right? So that should be moving to the left. And what about water? If we're increasing the concentration of water, right? Yeah, that should move to the right again. And what if we're decreasing the concentration of water? That should move to the left, right? Because we're draining the water, the reaction is going to flow to then make more of that water. What if we look at the products in this case, right? So what if we look at HOCl? If we increase that, which way is the reaction going to move? Left or right? Left, right? Because we're going to move towards the reactants if we're adding more products to the solution. What about for decreasing that? That'll then move to the right. And then for the chlorine ion, looks like there's a reading error there. If we increase chlorine, which direction is it going to move? It's going to move to the left, and then decrease it. It should then move to the right. Right, so the Chatelier's principle, if we're changing the concentration, the reaction will move in the direction that restores that ratio of concentration of products and reactants. So if we look at the concentrations, we can see it that way. And then on Thursday, we'll finish up talking about how does pressure affect, right? So pressure is only going to affect gaseous reactions. And what we're going to find is that increasing the pressure is like decreasing the concentration, right? Because we're changing the volume. If we increase the pressure, we can think of it in terms of a piston like this. We're decreasing the volume as we increase the pressure, which means the side of the reaction that has more moles of gas, right? That concentration of that is going to be increasing. So the side that has more moles of gas, the concentration is going to be increasing more than the side that has less moles of gas. So we're going to move in the direction to less moles. And then we'll talk about temperature as well. Okay, so it's could be potentially a lengthy lab today, so we'll start at 10:55 in lab. So take a break, go get